Anyway, it's all just stuff like this.
We move that out of the way. There we go.
Okay, you're on.
So we have here a two-level cross-sectional analysis using SPSS. If we look at this data set, you can see that subjects are nested in classrooms. There are 50 classrooms and 1,000 subjects total. These should actually be changed to nominal variables because they are identifiers only of subjects nested in classrooms. We have a continuous variable of math achievement, which varies from subject to subject. That will be our outcome variable. We have family SES, which varies from subject to subject. So we know that that is our level 1 predictor because it varies from subject to subject. And we have teachers' years of experience, which you can see is a constant for every subject in classroom 1. 28 years of experience for every subject in classroom 1, and for those subjects in classroom 2, their teacher had 26 years of experience. Becomes a constant across subjects within classroom. That's one of the ways that you identify that it is the level 2 predictor. So to begin, we go to Analyze, Mixed Models, Linear. We identify the nesting structure. You can put subject ID and classroom both over, but you really only need classroom. You just need to identify what the nest is, and the nests are classrooms. Continue. Our dependent variable is math achievement. We have 2 covariates available. Family SES, which is our L1, level 1 predictor, and teacher years of experience, which is our L2, level 2 predictor. We don't have any factors. Factors would be dichotomous, nominal, or polytomous variables, and we don't have any of those right now. The first thing we are going to do is establish which statistics we want. So we're going to take parameter estimates for fixed, tests for covariance parameters, and covariance of random effects. Those are the first 3 statistics we're going to ask for. Now, at this point, I just want to see what the mean and the variance of math achievement is. And so I'm not going to add anything into my combined equation at this point other than to ask for the mean and the variance. SPSS thinks in terms of the combined equation. And so when you see this fixed subroutine, it's adding components to the fixed portion of the combined equation. When you see this random subroutine, it is adding components to the random or the stochastic side of the combined equation. But right now, we're only going to ask for the mean and the variance. Now, it's going to give us an error message, but we will override that. It's going to say, hey, you didn't specify a model. Yes, I know I didn't specify a model. Go forward anyway, say no. And you see that I have a 2-parameter model. And the 2 parameters are really the 2 components of my combined equation, the very most simple equation you can have, which gives me an estimate of the intercept, 191. That's the average math achievement score across all subjects, across all groups, and the variance of the residual 4255. That's the variance of the residuals EIJ. This is the most simple model. And the reason I do this is so that I have a sense of my original amount of variance that I'm trying to explain. It gives me a baseline. It helps me know if I make any other mistakes, if things become very wrong in my next steps, and it doesn't square with that, then I know I've made a mistake. But right now we're dealing with 4,255 units of variance. Our next step is to create the null model, sometimes called the analysis of variance model. We go to mixed model, linear, establish still the classroom as the nest, and we're going to create our first random component in the combined equation, which is UOJ. We're going to ask whether or not there is significant variance among the group means around that grand mean intercept. So we go to random with, say, include intercept. This is not required, but it's a good habit to ask for main effects only. And we need to establish what the nest is, what the combinations are. This becomes more complex when we have three-level or longitudinal modeling, but for now, this is adequate. We'll say continue. Now, we should be expecting 3 parameters to be estimated when we say okay. And you can see we have 3 parameters estimated. We know that we're going to have the intercept gamma naught naught, and we're going to have the variance of EIJ, the variance of the residuals, and we're going to have the variance of the intercept or the variance of UOJ in our combined equation. This is really asking the question, is there a nesting effect? Here's our intercept, 191, and here are the 2 variance terms that have been estimated. The variance of EIJ or the variance of the residual, 1095, and the variance of the intercepts or the variance of UOJ, 3220. Those 2 combined should approximate what was the original variance estimate. The original variance estimate was 4255. And here we have something quite similar. It's not a computed value. These are estimated values, but we're in the ballpark. The question that is asked here is what percentage of the total variance is accounted for by variance between groups, and the variance between groups is the variance of the intercept 3220. If that's in the numerator and the original variance, or actually the sum of these 2 components, is in the denominator, we can see that 3 out of 4, so about 75% of the total variance is accounted for between groups. Now, this is a simulated data set. You will not often see that high of a ICC or percentage of the variance accounted for between groups. We're usually looking for a rule of thumb as above 0.06, and here we have 0.75-ish. So we know that we certainly have enough variance among the groups in terms of their intercepts to go forward. There is a strong nesting effect. The other way to get an estimate or a sense of whether or not there's an nesting effect is whether or not the variance of the intercepts is significantly different than 0. If it was not significantly different than 0, then we would know that really all the groups have about the same intercept. So our next step then is to add our first level 1 predictor. Now in this data set, we only have one level 1 predictor, but we could have mini. Our first level 1 predictor is going to go on the fixed side of the combined equation, and it's family SES. We'll add that. And we have just added in SPSS mind and in my mind a component to the combined equation, which will be gamma 1 naught family SES. We're expecting now 4 parameters because we have gamma naught naught, the grand intercept, gamma 1 naught, family SES, our first predictor, will maintain U naught J, and we will maintain EIJ in the combined equation, but we'll only get the variance terms for those stochastic components. We should get 4 parameters, which is what we have. That's terrific. And now you see that because we've added a predictor, the intercept is different, which is very common in multiple regression. As you add predictors, the intercept may change. And we're asking the first question, is the fixed effect of family SES a significant predictor of math achievement? And the estimate is 3.2, but it is significantly different than 0. This is a significant predictor, and it is positive, which means that for every 1 unit change in family SES, you will get 3.2 units increase in math achievement. It's a positive predictor. And then we'll look at our variance components and see that they're both still significantly different than 0, but look at that total now, 3264 plus 217. We have significantly, perhaps the wrong term, but clearly reduced the variance around the intercepts, the variance of the residual, by adding 1 predictor. We are beginning to explain why the variance from subjects to the grand mean is happening. And that's a good predictor. It was a significant predictor. Great. Our next step is to then free the slope of that predictor. The question we're asking here is whether or not all the groups have the identical slope. We know they have different intercepts, but we don't know whether or not family SES means the same thing in every classroom. Are the slopes different across classrooms? Or another way to say that is there significant variance in the slopes of family SES? So we simply go to random. We're going to add a random component beyond the intercept. Here we had the UOJ. Now we're going to add the component into the combined equation of U1J times Xij. Family SES as a random component, also known as freeing the slope. We should get 5 parameters estimated, and we do have 5 parameters estimated, so we did that correctly. Here are our estimates. We see that the intercept stayed at 77. The average effect or the fixed effect of family SES is still 3.2 units. That's the average slope across all groups. We see that the variance of the residual, the variance of the intercept, which we've estimated in the past, and now here's our new component, the variance of the slopes. It's 2.43, which is significant, which means that there is significant variation in the slopes of family SES as a predictor of math achievement across groups. That is a significant variance term. The groups don't all have the same slope. Terrific. Our next step is then to add the main effect of our level 2 predictor. And this is a fixed effect. So in the combined equation, we are adding a new component, but it's a level 2 predictor. This would be gamma naught 1 W1. Continue. Say, okay. We should have 6 parameters because we're doing this in a piecemeal way, 1 parameter at a time. And we see that here's our intercept. Here's the fixed effect of family SES. And here's our new predictor, teacher experience, 0.27 units, not significant. As a main effect, it is not significant. So even though it is not significant, we would like to know whether it has any power to explain the variance in the slopes of the level 1 predictor. So to do that, we will create a cross-level interaction. And to do that, we simply add a cross-level interaction to the fixed side of the combined equation. It's a little bit tricky, but you have to build nested terms. You see that button, build nested terms? Click that button. Now we select the main effect for the level 1 predictor multiplied times the main effect of the level 2 predictor. That creates the interaction term we're looking for, cross-level interaction. Add that to the combined equation. So now we have 3 components in our combined equation. And we know that we have asked for 3 components in the stochastic side of our combined equation. We should be expecting 6 parameters to be estimated. And we just did 6. You'll have to edit that, Ken. We should be expecting 7 parameters.
You can't edit
That's okay. We now have 4 fixed effects. We have the intercept, family SES, teacher years of experience, and the cross-level interaction, which is significant. That's important. That means that it is explaining some of the variance in the slopes. And in fact, if you look at the variance in the slopes of family SES, you will see that it has been reduced from the previous model. If you have a significant cross-level interaction, you then have to graph it. Can you pause this?